YouTube homework 5. Um, Draw an arrow for each glider and for system C to represent the direction of the change in moment. So this is my glide A. This is before, after. This is glide B. So initially it was at rest, so there isn't any magnitude to it. So after would be pointing to the right, and this is system C. The whole system would be pointing to the right. So the moment vector is pointing in the same direction as the velocity vector. The change in moment is the same as the direction in which the glider gliding at. So, is the magnitude of the change in moment vector for glider A greater, less than, or equal to the magnitude of the moment for glider B? So I said that the change in moment for A and B are equal. The impulse is the same but different direction for both of them, so the momentum is conserved since there's no external forces. So B, draw an arrow for each glider to represent the direction of change in velocity from before to after the collision. So for glider A, I have the before pointing to the right, after pointing to the left, and for glider B, the before is a point and after should be a vector pointing to the right. So the velocity is just the direction in which the block fly, and the direction is stated in the question where the block are gliding. So yeah, A is to the left and B is at rest and to the right. Is the magnitude of the change in velocity vector for glider A greater than, less than, or equal to the magnitude of the change in velocity for vector glider B? So I said that the magnitude of change in velocity for glider A is greater than that of glider B, assuming that momentum is conserved. M1v1, we have the equation M1v1 equal to M2v2. So a smaller mass will require a bigger velocity in order to have the same momentum as the bigger mass. Okay, so the statement is incorrect because the momentum of two interacting objects are proportionally related to one another by the equation m1v1 equal to m2v2. So if the velocity of one decreases, the other velocity would decreases as well, assuming that the two masses doesn't change. Number 2 is the net force on the left piece always 0? No, it is accelerating, and by Newton's second law, there has to be a force in the direction of the acceleration. So the F net cannot be 0. Is the net force on the system consisting of both pieces always 0? Yes, they exert forces of equal magnitude on one another with opposite direction by Newton number 3 pair. So the forces cancel out because they're internal forces. Is the momentum of the left piece conserved? No, its velocity in the beginning is 0, but now it has some velocity, assuming that the mass stayed the same. Therefore, momentum is not conserved. Is the momentum of the system consisting of both pieces conserved? Yes. The velocity of the two pieces are moving with the same velocity, but in the opposite direction. So the velocity and the momentum vector cancel out one another, and we're left with 0 velocity and 0 change in momentum. B, a block slide down a frictionless incline. The incline is fixed in plane on a table. So no, the net force is not 0 because the block has some acceleration And again, by Newton's second law, they have to be a force in that direction. Is the net force on the incline always zero? Yes, so the incline is at rest, so there is no acceleration. And by Newton's second law, the F net have to be zero due to zero acceleration. Is the net force on the block incline system always zero? No. The net force of the system is not zero because one part of the system is moving while the other part remains stationary. And from my free body diagram, there was no force to cancel out the friction force of the uh, surface. Is the momentum of the block conserved? No, the momentum is not conserved. There's a force acting on it and the velocity is changing, so the acceleration not zero. Is the momentum of the incline conserved? Yes, the momentum is conserved. The mass and the velocity stay the same throughout the whole process. So momentum is conserved. Is the momentum of the block incline system conserved? No, there is a net force acting on the block. In order for the momentum to be conserved, there have to be a change in velocity for the incline as well to balance out the force on the block. C. Is the net force on the block always zero? No. The block is still sliding, accelerating, therefore there is a force acting on it. Is the net force of the incline always zero? No. In my FED for part B, there is a friction force to oppose the normal force of the box on the incline. So if there is no friction friction force, the block will accelerate, which means the net force is not zero. Is the net force on the block incline system always zero? Yes, there's now only a normal force and a gravitational force. There's friction like the other case. There is no friction like the other cases, which means that the F net of the system is equal to zero. Is the momentum of the block conserved? No, the momentum is not conserved since the net force is not zero and its velocity is changing. So the momentum initial is different from the momentum final. Is the momentum of the incline conserved? No, if there is no friction, the incline will start to move. Therefore, V final is different from V initial while mass remains the same. Therefore, momentum is not conserved. Is the momentum of the block incline system conserved? Yes, there is now the momentum is now conserved because there is now a change in the incline velocity. It cancels out the change in the velocity for the block. Part B. The net force on block A always zero. No, the string will pull on block A, which make it accelerate upwards. So by Newton number 2, the F net is different, zero. No. Is the net force on system S always zero? No, initially the system was at rest zero acceleration, but then there is some acceleration due to gravity. F equal ma, so if the acceleration is zero, not zero, then net force can be zero. Is the momentum of block A conserved? No, there's an external force acting on it, which causes its velocity to change. M1v1 different from M2v2, assuming that mass A stayed the same throughout, momentum is not conserved. Is the momentum of the system S conserved? No, initially there isn't any velocity to the system. Then it was at rest, but then it started to accelerate and change its velocity. So therefore, momentum for the system is not conserved. Number 3. In the space it provided, draw a moment vector for glider A, glider B, and system S. So this is my glider A, and the moment, the magnitude is m multiplied by v initial. This is my glider B. The moment is 2m multiplied by v sub b. This is my system S. This is and its magnitude is 2m plus m multiplied by v final. So part B, draw the vector in the space of the velocity for glider A and B in reference frame of glider X. So this is glider A. This will have 0 magnitude, which means that its velocity is v sub b, and glider B will move toward glider X, and it will has a negative v initial. The moment is just the same as the velocity, except there is a mass multiplying by the velocity up in each case. So the mass of glider X doesn't have anything to do with the momentum of A and B. So the momentum now is just the velocity in reference frame of glider X multiplied by the mass of A and B. So glider A will have 0 velocity v sub b since it is moving with glider X at the same velocity, while glider B will have a negative v naught moving to the left. So explain the error in the Sen reasoning. So I think that the mass of glider X doesn't have anything to do with the problem, only its velocity does, because point of reference doesn't deal with mass of the observer. Conceptually, we can think of momentum as how hard it is to stop some. So when you're moving with the object with the same speed, you can see that the object is already not moving, so there shouldn't be any momentum to stop it from moving. So suppose glider X had a different mass. Would the magnitude of the momentum of glider A in the reference frame be the same or different? So the magnitude of momentum of glider A would be the same because reference frame depend only on the velocity of the moving object and not its mass.